Hello, my name is Chunyoung Sung, and I'd like to present our paper, CRIT, Graph-Based Automatic Data Synthesis to Enhance Cross-Modal Multi-R Reasoning. CRIT proposes a graph-based framework for automatically generating cross-modal multi-reasoning datasets, and training on the generated dataset improves cross-modal reasoning and standard multimodal performance in vision language models. Starting from the motivation, real-world tasks often involve reasoning over interleaved sources of information from multiple modalities. Such task is defined as cross-modal multi-R reasoning. For example, when reading a scientific paper or a DIY tutorial, when a question is given that requires information from both images and text, we need to locate the necessary evidence from each modality and connect them to answer to the question. However, existing RealMs lack such ability due to scarcity of data. Manual collection and annotation is too expensive, so we address this problem by creating a scalable automatic pipeline for generating high-quality cross-modal multi-reasoning data. Our dataset covers interleaved image text and multi-hop reasoning for diverse data sources. The entire dataset is generated by an LM, where the test set is verified by human experts. For each sample, also the reasoning traces exist, and in total of 271K samples has been generated. Moving on to the methodology, we use the LMs throughout the entire data generation process for automation. Key properties of our pipeline includes the graph, where graph captures entities, attributes, and relationships from both visual and textual modality. Subgraph sampling ensures complex multi-R relationships, and models generate questions and answer pairs from the sampled subgraph, which require cross-modal multi-R reasoning. Without using a graph and directly prompting an LM, fails to generate QA pairs that requires cross-modal multi-R reasoning. This is because LMs often generate questions that relies only on one modality, or where questions collapse multi-R reasoning into a shallow single-hop relation. Our pipeline consists of 3 stages: multimodal content graph construction, which starts from image dataset and scene graph annotations, with LMs generating new nodes and edges that serves as textual contents. Next is textual contents generation, where the subgraphs are extracted from the multimodal content graph to produce complementary textual descriptions. Finally, it is the question-answer generation, where subgraphs are further sampled to generate QA pairs that require cross-modal multi-R reasoning. We further extend this pipeline to videos and text-rich sources. This is because the existing pipeline is limited by the need for pre-annotated graph images, independent and unrelated images, and it mostly focuses on natural images. We extend the pipeline by deriving graphs from alternative annotations. The new data sources consist of video frames and scientific papers with abundant text-rich images. For videos, instead of using the pre-annotated scene graph, we convert the video captions to a graph. From the video, we extract frame per caption using clip similarity, and after graph construction, the rest of the pipeline remains the same as before. For scientific papers, they naturally provide aligned image text contents, so there is no need to further generate extra textual descriptions. We convert all multimodal content into a unified graph, and figures in rendered tables are treated as images. For the content graph, the textual entities and relations are extracted from paragraphs not referring to figures in tables, and the visual entities and relationships are extracted from paragraphs referring to figures in tables, where the visual entities and relations means numerical data, comparisons, and visual descriptions. After extracting such visual information, we remove such sentences once the information is captured as graph elements, since these should be inferred from the visual modality. Moving on to the results. This slide has the results for the performance on the CRIT test sets. The tables show that both proprietary and open source VLMs, including reasoning models, perform poorly, while models trained with their training sets created by the automatic pipeline perform well on all domains. We further extend our dataset by using model-generated scene graphs instead of human-annotated scene graphs. And after training with the extended dataset, the model performance is further improved. We compared performance of VLMs and the same model fine-tuned on Mantis Instruct alone or jointly with CRIT to show how models perform on external benchmarks when trained with CRIT. As a result, models trained with CRIT has increased performance on both cross-modal benchmarks and also on standard multimodal benchmarks as well. We also have manually examined 75 error cases from GPT-4o on CRIT to analyze why models fail to complete on cross-modal multi reasoning tasks. There are four types of errors: evidence localization, visual perception, textual comprehension, and answer generation. As below, most of the error consists of evidence localization and visual perception. This means that models fail to perform on cross-modal multi reasoning because they fail to locate where the evidence necessary to complete the task is, and even if they do, they have hallucination in terms of visual perception. To conclude, our contributions are in proposing an automatic graph-based data generation framework, the creation of the CRIT datasets, and empirical improvements via training with the CRIT datasets. Thank you for listening.